Hello friends, till now in our discussion on electromagnetism, we have discovered that a moving charged particle produces a magnetic field around itself. Thus, a current of moving charged particles produces a magnetic field around the current. This feature of electromagnetism, which is the combined study of electric and magnetic effects, came as a surprise to the people who discovered it. Surprise or not, this feature has become enormously important in everyday life because it is the basis of countless electromagnetic devices. Our first step in this lecture is to find the magnetic field due to the current in a very small section of current carrying wire. Then we shall find the magnetic field due to the entire wire for several different arrangements of the wire. Calculating the magnetic field due to a current. Figure shows a wire of arbitrary shape carrying a current I. We want to find the magnetic field at a nearby point P. We first mentally divide the wire into differential elements and then define for each element a length vector that has length differential element and whose direction is the direction of the current in a differential element. We can then define a differential current length element to be IDS. Here we wish to calculate the differential element of magnetic field produced at P by a typical current length element. From experiment, we find that magnetic fields, like electric fields, can be superimposed to find a net field. Thus, we can calculate the net magnetic field at P by summing via integration the contributions of differential element of magnetic field from all the current length elements. However, this summation is more challenging than the process associated with electric fields because of a complexity, whereas a charge element dq producing an electric field is a scalar, a current length element producing a magnetic field is a vector, being the product of a scalar and a vector. So the magnitude of the differential element of magnetic field produced at point P at distance r by a current length element turns out to be dB is equal to mu 0 upon 4 pi into I ds sin theta divided by r square. Here theta is the angle between the directions of differential element and unit vector, a unit vector that points from ds towards P. Symbol mu 0 is a constant called the permeability constant. The direction of differential element of magnetic field showing as being into the page is that of the cross product of differential element and unit vector. We can therefore write equation A in vector form as dB is equal to mu 0 upon 4 pi into I ds into unit vector divided by r square. This vector equation and its scalar form, that is equation A, are known as the law of Biot and Savart. The law which is experimentally deduced is an inverse square law. We shall use this law to calculate the net magnetic field produced at a point by various distributions of current. Magnetic field due to a current in a long straight wire. We shall now prove using the law of Biot and Savart to prove that the magnitude of the magnetic field at a perpendicular distance r from a long infinite straight wire carrying a current I is given by B is equal to mu 0 I upon 2 pi r. The field magnitude B in equation C depends only on the current and the perpendicular distance r of the point from the wire. We shall show in our derivation that the field lines of magnetic field form concentric circles around the wire. The increase in the spacing of the lines with increasing distance from the wire represents the 1 upon r decrease in the magnitude of magnetic field predicted by equation C. The lengths of the two magnetic field vectors in the figure also show the 1 upon r decrease. Plugging values into equation C to find the magnitude B at a given radius is easy. What is difficult for many is finding the direction of a magnetic field vector at a given point. The field lines from circles around a long straight wire and the field vector at any point on a circle must be tangent to the circle. That means it must be perpendicular to a radial line extending to the point from the wire. But there are two possible directions for the perpendicular vector. One is correct for current into the figure and the other is correct for the current out of the figure. How can you tell which is which? Here is a simple right-hand rule for telling which vector is correct. Grasp the element in your right hand with your extended thumb pointing in the direction of the current. Your fingers will then naturally curl around in the direction of the magnetic field lines due to that element. To determine the direction of the magnetic field set up at any particular point by the current, mentally wrap your right hand around the wire with your thumb in the direction of the current. Let your fingertips pass through the point. Their direction is then the direction of the magnetic field at that point. In view of the figure 1, magnetic field at any point is tangent to a magnetic field line. In the view of figure 2, it is perpendicular to a dashed radial line connecting the point and the current. Proof of equation. This figure here is just like the figure we used early in the lecture to find the magnetic field due to a current, except that now the wire is straight and of infinite length, illustrates the task at hand. We seek the magnetic field at point P, a perpendicular distance r from the wire. The magnitude of the differential magnetic field produced by P by the current length element IDS located a distance r from P is given by equation A. The direction of differential element of magnetic field is that of the vector ds into unit vector r directly into the page. Note that differential element of magnetic field at point P has the same direction for all the current length elements into which the wire can be divided. Thus, we can find the magnitude of the magnetic field produced at P by the current length elements in the upper half of infinitely long wire by integrating differential element of magnetic field dB in equation A from 0 to infinity. Now consider a current length element in the lower half of the wire, one that is as far below P as is above P. Then by equation B, the magnetic field produced at P by this current length element has the same magnitude and direction as that from the element IDS. Further, the magnetic field produced by the lower half of the wire is exactly the same as that produced by the upper half. To find the magnitude of the total magnetic field at P, we need to only multiply the result of our integration by 2 and we get B is equal to 2 into integral of dB from 0 to infinity, which comes out to be equal to mu 0 I upon 2 pi into integral of sin theta ds divided by r square. The variables theta, s and r in this equation are not independent. Figure shows that they are related by r is equal to under root of s square plus r square and sin theta is equal to sin pi minus theta, which is equal to r upon under root of s square plus r square. With these substitutions and solving integral, equation D becomes B is equal to mu 0 I upon 2 pi r. Magnetic field due to a current in a circular arc of wire. To find the magnetic field produced at a point by a current in a curved wire, we would again use equation A to write the magnitude of the field produced by a single current length element, and we would again integrate to find the net field produced by all the current length elements. That integration can be difficult depending on the shape of the wire. It is fairly straightforward, however, when the wire is a circular arc and the point is the center of the curvature. Figure A shows such an arc shaped wire with central angle phi, radius r, and center C carrying current I. At C, each current length element IDS of the wire produces a magnetic field of magnitude dB given by equation A. Moreover, as figure B shows, no matter where the element is located on the wire, the angle theta between the current length element vectors and unit vector is 90 degrees. Also, small r is equal to capital R. Thus, by substituting capital R for small r and 90 degrees for theta in equation A, we obtain dB is equal to mu 0 upon 4 pi into I ds sine 90 degrees divided by r square, which comes out to be mu 0 upon 4 pi into I ds upon r square. The field at C due to each current length element in the arc has this magnitude. Direction of the differential field. From the previous discussion, we now know that the vector must be perpendicular to a radial line extending through point C from the element either into the plane or out of it. To tell which direction is correct, we use the right hand rule for any of the elements as shown in figure C. Grasping the wire with the thumb in the direction of the current and bringing the fingers into the region near C, we see that the differential field vector due to any of the differential elements is out of the plane of the figure, not into it. To find the total field at C due to all the elements on the arc, we need to add all the differential magnetic field vectors. However, because the vectors are in the same direction, we do not need to find components. We just sum the magnitudes of field vectors, that is dB, as given by equation E. Since we have a vast number of those magnitudes, we sum via integration. We want the result to indicate how the total field depends on the angle of the arc rather than the arc length. So, in equation E, we switch from ds to d phi by using the identity ds is equal to r d phi. The summation by integration is then given by this equation. Integrating, we find that b is equal to mu 0 I phi divided by 4 pi r. Forces between two parallel currents. Two long parallel wires carrying current exert force on each other. The figure here shows two such wires separated by a distance d and carrying currents IA and IB. Let us analyze the forces on these wires due to each other. We seek first the force on wire B due to the current in wire A. That current produces a magnetic field, and it is this magnetic field that actually causes the force we seek. To find the force, then, we need the magnitude and direction of the field at the site of wire B. The magnitude of magnetic field at every point of wire B is then BA is equal to mu 0 into IA divided by 2 pi into D. The curled straight right hand rule tells us that the direction of magnetic field due to wire A at wire B is down. Now that we have the field, we can find the force it produces on wire B. The force on a length L of wire B due to the external magnetic field produced by wire A is given by FBA is equal to IBL into BA. In figure, vectors L and BA are perpendicular to each other, so we can write FBA is equal to IBL BA sine 90 degrees, which is equal to mu 0 into L IA IB divided by 2 pi d. The direction of force vector is the direction of the cross product of the length of wire and the magnetic field due to wire A. Applying the right hand rule for cross products to the length of wire and the magnetic field in, we see that the force is directly towards wire A. The general procedure for finding the force on a current carrying wire is then first find the field due to the second wire at the site of the first wire, then find the force on the first wire due to that field. We could now use this procedure to compute the force on wire A due to the current in wire B. We would find that the force is directly towards wire B. Hence, the two wires with parallel currents attract each other. Similarly, if the two currents were anti-parallel, we could show that the two wires repel each other. So friends, here we come to the end of our discussion in this lecture today, and therefore we sum up. The magnetic field set up by a current carrying conductor can be found from the Biot-Savart law. For a long straight wire carrying a current I, the Biot-Savart law gives the magnitude of the magnetic field at a perpendicular distance r from the wire. Parallel wires carrying current in the same direction attract each other, whereas parallel wires carrying currents in opposite directions repel each other. So that is it for today. See you in the next lecture, where we shall be discussing Ampere's law. Thank you very much.